Ladies and gentlemen, I welcome you to the Historical Acoustic-Phonetic Collection of Technische Universität Dresden. My name is Rüdiger Hoffmann. I represented the field of system theory and speech technology here until I retired. And from that, you can already see the connection to what this collection conveys, namely, the history of processing speech by electronic means. In the past, this was always difficult to communicate because the field itself had a somewhat difficult time. Synthetic speech was hard to understand, and speech recognition did not really work properly. Over many decades, this has improved, and today speech-based communication systems are already part of everyday life for many people. That means that today one no longer really has to explain the purpose and meaning of this discipline. People generally know it now. This field has been pursued at TU Dresden since the 1950s. My predecessor at the time, Walter Tscheschner, started here as a student, then dealt in his diploma thesis with questions of speech processing in communications engineering, remained at the university afterwards, and in 1969 became professor of speech communication. That is a relatively early point in time for establishing this subject at a university, and we are quite proud of that. This history, which now extends over more than 7 decades, can be documented by means of various exhibits. That is one of the aims of this collection. But if you look at the background in front of which I am standing now, you may first ask yourself, this is not electronic at all. So what is it doing here? And it is indeed the case that there are exhibits here which reach back much further than the electronic era itself. These are exhibits from early experimental phonetics from the end of the 19th century. These exhibits did not originally come from the Faculty of Electrical and Computer Engineering here at this university, but from phonetic institutes. 2 very important earlier phonetic institutes should be mentioned here. One is the Institute of the University of Berlin. It goes back to the work of Hermann Gutzmann Sr., who at the end of the 19th century created the connection between pedagogy and medicine, which later found expression in the institutionalization of the field of logopedics. In 1906, he then had the opportunity to move to the Charité in Berlin. This laboratory goes back to that period, and the exhibits are here today. A second very important phonetic institute was that of the so-called Colonial Institute in Hamburg. It was a predecessor of today's University of Hamburg and was established before the First World War, at a time when colonies still played a role for Germany. This institute had a phonetic laboratory. It was directed by Giulio Panconcelli-Calzia, a very important experimental phonetician of his time. He worked there for many decades. And after the Hamburg chair was dissolved, the holdings from that laboratory also came here. As a result, we are able, in a unique way, to document the development of speech technology from its beginnings in experimental phonetics, practically up to the entry of computers into the laboratories. After that, we stopped. You will therefore not see any personal computers here that are somehow equipped with speech technology. For me, that is a question of computer science, and it does not concern us here so much. The collection itself, with about 1,000 exhibits, displays the greater part of its holdings in 3 showrooms. In the first one, where we are standing now, the room is devoted to experimental phonetics, and I will say a few more words about it in a moment. Then there is a second room, which is devoted to speech synthesis, and a third room is devoted to speech analysis and recognition. We will visit both of those afterwards. In our exhibition room for experimental phonetics, we have set up 4 display cases in which the most beautiful or most important exhibits are gathered, so that one can give a brief overview. In our first display case, we are dealing with one of the roots of experimental phonetics. Experimental phonetics arose at the end of the 19th century, not out of nothing, but because there were demands from various directions to develop phonetics further. One of these roots was experimental medicine, especially physiology. One must remember that in the 19th century, especially in the first part of the 19th century, medicine itself was only then developing further on a scientific basis. At that time, especially in the field of physiology, there were several scientists who pursued the idea of explaining the human being with the help of physics and chemistry, and not with any vague concepts. Among them was, in particular, Hermann von Helmholtz. The 2 exhibits in this display case remind us of him. Later generations know Helmholtz more as a physicist, because he later held the chair of physics in Berlin. But before that, he worked a great deal in the field of physiology, especially in Heidelberg. And in 1863, he wrote a pioneering book on the sensations of tone, in which everything that was known about hearing up to that point was collected. In that context, he introduced resonators as measuring instruments, which are now named after him, the so-called Helmholtz resonators. Here we have a beautiful and visually very attractive set. Such a Helmholtz resonator is based on the fact that a volume produced in this way, in a special combination with a neck or tube, has a resonance frequency. One can therefore calibrate such resonators for certain frequencies. And when one holds such a resonator to the ear, using the small tip at the top, and hears that this resonator really begins to resonate, then one can be sure that this particular spectral component was present in the sound that one was acoustically receiving at that moment. In this way, one can measure a spectrum piece by piece, and for that time this was an important advance in measurement technology. In addition to these Helmholtz resonators, a small model of the middle ear also recalls that period. Everyone knows that in connection with the eardrum there are 3 small auditory ossicles in the middle ear: the hammer, anvil, and stirrup. In the 19th century, a great deal of research was done on this. This small model shows these ossicles in motion. One can press on the eardrum, and then everything moves as it should. This model dates from around 1870 and was made by Heinrich Sittel. There are 3 examples of it worldwide. And Heinrich Sittel, if one looks it up, was a laboratory assistant of Helmholtz at the time when Helmholtz still had the Physiological Institute in Heidelberg. So I always add at this point that it is not certain that Helmholtz personally held this object in his hands, but his gaze certainly rested on it, and in that sense this is the icon of our collection. This second display case recalls another root of experimental phonetics, one that is to be found more in the therapeutic or medical field. It actually goes back to what was then called the education of deaf-mute people. Around the turn from the 18th to the 19th century, it had been understood that deaf people were capable of education, and that the way in which they had been treated up to that point was absolutely not justified. And so the demand arose toward phonetics, provide us with teaching aids, and first explain to us how speaking works, so that we can explain to deaf people what they have to do. This development was very fruitful. What we can show here in this display case are two exhibits that are somewhat later. In the end, they describe the work of the speech therapist or speech healing practitioner. A row of tuning forks such as this one stands for audiometry, which today we know with electronic means, that is, the measurement of a patient's hearing ability. Originally, this was done by taking tuning forks, one separate tuning fork for every semitone of the musical scale. That meant a large cabinet full of heavy equipment, a so-called tonometer. Then, in 1890, there was an invention by the otologist Bezold in Munich, together with the physicist Edelman. They developed a series of tuning forks that had movable weights on the prongs and were calibrated accordingly, so that one could read off which tone was produced at which position of the weights. In this way, the entire scale could be realized with far fewer tuning forks. In addition, an apparatus for measuring respiratory volume is shown here, which the corresponding physician, of course, also needed. This volume meter had the special feature that a writing stylus could be attached to it at the top, and with this stylus, one could record on a kymograph how the respiratory volume changed during the process being measured. And with that, we have already arrived at the next display case. This display case deals with recording technology. If one wants to research speech, one has to record and preserve it somewhere. Speech is a fleeting event. One naturally thinks first of Edison's invention, the phonograph of 1878, which could record sound on cylinders, and then 10 years later of Berliner's invention of the gramophone. Only since that time do we know authentically how our predecessors spoke. Of course, because these recordings can also be played back, one can also try to enlarge the grooves or traces on the sound carrier and derive from them a signal for further research. But that is extremely laborious and technically difficult. For this reason, in phonetics, whenever it was not a matter of being able to listen to the recordings again, people tended instead to fall back on the invention of the so-called kymograph. Here's an example. The kymograph records vibrations on a rotating drum, which was usually covered with smoked paper, so that a stylus could scratch a time function into the soot, and the whole thing was fixed afterwards. The kymograph in this form dates to the year 1847. In itself, the principle is older, considerably older. It is also an obvious idea to use a rotating drum for recording. But in 1847, Carl Ludwig, one of those famous physiologists and a kindred spirit of Helmholtz, was carrying out investigations of blood pressure, that is, of the human blood system, and he recorded blood pressure. He did this in a way somewhat similar to the way one uses a blood pressure cuff today. He directed the pressure fluctuations to a mercury manometer. On top of the mercury surface, he floated a kind of little boat that had a pointer attached to it. This pointer then scratched onto such a kymograph drum. And although, as I said, this technology was in principle known, he somehow hit a particularly suitable moment. Suddenly, everyone wanted to have this for their investigations, and that is the birth of the kymograph. Now, Ludwig had a mechanic, Gerhard Baltzar, who was evidently very talented, and he developed this idea of the kymograph further into a device ready for serial production. The kymograph, according to Ludwig and Baltzar, then became a standard instrument. We have already seen the standard version, a large and heavy device, in the picture earlier. Here, so that it fits into the display case, there is a so-called travel kymograph according to Zuntz. It is somewhat reduced for that purpose, but also light enough in weight that one could take it on expeditions, for example. It was then necessary somehow to create a possibility of transferring the time function that one wanted to record into a movement of a pointer. And there was already, from the medical era and from this blood pressure context, the so-called Mary capsule. You can see it here. A pressure fluctuation is supplied from somewhere through a tube, and in this capsule, the pressure fluctuation is then naturally present. The capsule has a membrane at the top, and on this membrane, which moves accordingly, this small straw pointer is fixed. One can easily imagine that this works well for low-frequency processes. In this example, one sees the recording of respiratory movements during speaking. There is one belt for the chest, for chest breathing, and another belt lower down, intended for abdominal breathing. The corresponding fluctuations are then recorded here with large amplitudes. You can see that on this example, which is stretched out here. Everything is clearly visible and very easy to interpret. The whole thing becomes difficult, however, when we have higher frequencies. And by higher, I already mean the frequencies that occur in speech. For example, the laryngeal vibration on the order of 100 Hz, and then, correspondingly, the formants in speech, which are considerably higher still, in the hundreds and thousands. These frequencies can hardly be represented in this way. Very special capsules were made for that, which were very light and still had a reasonably acceptable upper frequency limit. With these capsules, direct recordings of sound were made, which had very small amplitudes but were, in principle, still analyzable. The analysis of the recordings obtained, especially those obtained with the kymograph, was an important occupation for phoneticians of that period and was very laborious. One needed, one might say, an immense amount of patience to measure and evaluate the recordings period by period and so on. One can imagine that an important function in the analysis of speech recordings was to measure the course of pitch, that is, the frequency of the laryngeal vibration. In itself, this can be done quite simply by measuring the duration of a period, and then the frequency is merely the reciprocal of the period duration. But once one has done that 10,000 times, it becomes a very tiring activity. Nevertheless, the scientific foundations of what we know today about speech essentially arose in that period, and essentially through such painstaking work. That is something one should think about from time to time. In order to make this work somewhat easier, the most diverse, ingenious instruments were invented, and a large part of the exhibits in this room can be assigned in some way to these forms of analysis. Some of this is quite complicated to explain and goes far beyond our goal here. Something that can be interpreted quite well is this so-called pitch measuring apparatus, which was used at the time. Here, under this magnifying glass, recordings of speech are placed, which unfortunately are characterized by very small amplitudes. They are then measured with a kind of micrometer screw. And so that one at least saves oneself the inversion. There is a template up here, which in the end imitates the function 1 over x. With it, one can graphically record the course of the fundamental frequency. At the time, that was already a great help. It is correspondingly complicated if one wants to calculate Fourier coefficients, that is, if one wants to determine the speech spectrum. The pioneering work by Fourier, in which the formulas for calculating the coefficients are given, had already appeared in 1822, and it also satisfied an important need in physics in particular. That means that for almost the whole 19th century, these integrals were already being calculated, numerically in some way, and naturally all kinds of ideas were developed to simplify this difficult work. Many analog calculating machines were produced for this purpose. The simplest idea for the whole matter came from George Udny Yule, who later became known as a statistician. There was a harmonic analyzer, according to Yule, although it was not really ready for serial production. Then, in Germany, Audiometry, who later was actually an aircraft engineer and incidentally also an honorary doctor of the Technical University here in Dresden, brought this instrument to serial maturity. This harmonic analyzer, according to Mader, which is here in this case in a disassembled state, was in itself the standard instrument for calculating Fourier coefficients until, and one really has to savor this, into the 1960s. As is well known, the fast Fourier transform was invented in 1965, and only since then has a computerized calculation of Fourier coefficients become the method of choice. There are certainly still people alive today who say, yes, during my student days, I still calculated Fourier coefficients with this apparatus. So, with that, we have finished a brief overview of the research work of phonetics. Among the devices and objects from this period, one also finds many that were not devoted to research, but to teaching. They simply illustrated for prospective phoneticians how human speech works. We will now turn to those by looking at what can be said about speech synthesis, about the production of speech, first by human beings and then by machines. There are quite a number of anatomical models in our collection which illustrate how the human being produces speech. This head stands here as an example. What we have to note in the following is something that everyone actually knows. The process of speech production in humans is a two-stage process. First, with the larynx, which is located down here, or more precisely with the vocal folds, one produces a signal. This signal is variable in pitch, but otherwise it must first be shaped into speech by passing through the articulatory tract. That is the throat and oral cavity, closed off by the lips. In addition, there is the nasal tract, the nasal cavity, which can be connected when necessary. There are therefore many possibilities for modifying the signal produced by the larynx. In technical terms, one speaks of the combination of source and filter. That is, of course, terminology from communications engineering. But communications engineering, at the time when electronics emerged, in any case took possession of speech synthesis to a considerable extent. We will explain that further later. At the moment, however, we are still here in the pre-electronic period. People first tried to reproduce this process, this combination of source and filter, mechanically, and these attempts date back quite far into the age of the Enlightenment. Here one should mention especially the famous mathematician Leonhard Euler, who once wrote that the artificial production of speech would be something very desirable. He was thinking more of sound projection in large rooms, churches, and things like that. He imagined something like a vowel organ, that is, some instrument on which one could press keys, and then the corresponding sound would be produced. That was, of course, rather simplified. But the idea behind it was, and he also expressed this, that a certain type of organ pipe, namely reed pipes, could be used to imitate articulation, the so-called vox humana register of the organ. This idea was taken up at that time by various people. The solution that has remained in memory, the one that has, in a sense, remained in memory to this day, is that of Wolfgang von Kempelen. He built a speaking machine based on this idea. He described this speaking machine in a book in 1791. And because it was described there so solidly, various people have also attempted to build replicas. There are indeed several replicas of this speaking machine, and the one we have here comes from Saarland University in Saarbrücken. The idea was, as with the reed pipe. Here we have an example of such a reed pipe. In the end, there is air flowing through, and this air has to pass a vibrating reed, such as one knows from a harmonica, for example. Depending on its geometry, it vibrates at a certain frequency and produces a broadband signal, just as the larynx or the vocal folds produce a broadband signal. This is necessary so that it can then be modulated accordingly. Wolfgang von Kempelen actually had other duties. He was a state official at the court of Maria Theresa, and in this function had an enormous amount to do. He pursued the construction of automata as a kind of compensatory activity, or however one wants to describe it, and in doing so, he devised this speaking machine. As I said, a simple bellows and vibrating reed in combination produced something like a neutral child's voice. He really did think of a child's voice, and wrote so. Connected to this wind chest with the reed, which is hidden inside here somewhat mysteriously so that not everyone can immediately see how it works, is ultimately a mouth. This is a part made of rubber that can be deformed so that the corresponding sounds can be produced. One can demonstrate quite a lot with it. I will make it very simple here. If one imagines what a small child does when it starts playing with its voice, then it says a vowel like ah, and then closes its mouth. If one alternates that, exactly what I get happens when I close and open the mouth here. In this way. And already with this simple word mama one can achieve effects. One can refine it a little. If one holds the nose closed, one can no longer make an M. Then a plosive sound arises, and with luck, one gets papa. Once again, something like that. The ability of such a mechanical structure to produce speech caused an enormous sensation at the time. Kempelen became famous with it, traveled around Europe, demonstrated this speech synthesis together with his well-known chess Turk, and in this way it became, so to speak, a milestone in the development of speech technology. This imitation, in other words source, and resonator, was later also used when it came more to the scientific description of speech. Here there is also a replica, an example from investigations by two Japanese researchers, Chiba and Kajiyama. They made resonators that approximately, or as precisely as possible, reproduce the shape of the vocal tract during the articulation of a particular vowel. They are therefore different from vowel to vowel. And here there is also a small pipe, inside which serves as a substitute for the larynx. Here we have a bellows of a somewhat more modern form. And when one combines these parts, a vowel comes out in this form. or another vowel. So much, very briefly, for mechanical speech synthesis. We will return to it briefly later, but first we turn to electronic speech synthesis, which gained importance after the Second World War. When one speaks about electronic speech synthesis, one has to begin with the vocoder. In fact, efforts to generate vowels by electronic means, for example, go back ultimately to the invention of the electron tube in 1906. But things became really interesting when communications engineering made the demand that speech be transmitted with as little bandwidth as possible, for reasons of cost. We know that speech is a relatively broadband signal. Human hearing, when one is young, reaches up to 20 kilohertz. For speech, one does not need quite so much, but for high-quality transmitted speech, one still needs something like 6 to 8 kilohertz. It does not have to be that high in every case. In telephony, for example, people agreed to transmit the range up to 3.4 kilohertz. And even that is, of course, a lot if one thinks economically and wants to make good use of transmission paths. For that reason, around 1930 there were already proposals, even the first patent in Germany, to extract parameters from the speech signal and transmit only these parameters. That would save a great deal of bandwidth, and on the receiving side, the speech signal would of course be put back together, that is, synthesized, from these transmitted parameters. Similar efforts existed in the United States and also in the Soviet Union. It was then carried out to perfection at Bell Laboratories in the United States, connected with the name of Homer Dudley. He also coined the name vocoder, from voice coder, for this device. During the war, the vocoder was used not because of bandwidth reduction, but because this parameterization also introduced an encryption of speech. The vocoder could therefore be used for eavesdropping secure speech transmission. For that reason, the latest state-of-the-art only became properly known after the war. The institutes in telecommunications engineering naturally then wanted to know whether this vocoder would also be useful in civilian life. The question was difficult to answer because with the technology of electron tubes at the time, these were huge devices prone to failure, and the benefit was not clear. The only real way to find an answer to this question was simply to build such a thing. Various telecommunications institutes worldwide did this at the same time. Among them, the Institute of Telecommunications Engineering, at what was then the Technische Hochschule in Dresden. This vocoder was built at that time by Eberhard Crocker. After completing his dissertation, however, he changed fields, and the whole matter then passed to Walter Tscheschner, whom I have already mentioned, and he remained involved with this subject. This enormous device from that period has unfortunately not survived. I can show here a vocoder from the 1960s. It comes from the company Sennheiser and was used in the Federal Republic of Germany to produce encrypted transmissions with diplomatic missions abroad. It is thus already a much later technical state, based on the use of transistor technology and so on. This device came here as part of an exchange of duplicates, and in this way I can at least show a vocoder, even if it is not the very old one. The vocoder was of enormous benefit for speech research, because it already represented a high stage of development in speech synthesis. One can say, a little casually, that with the vocoder the subject of speech synthesis, at least from the electronic side, was basically solved. One knew what was needed. This principle of source and filter was realized there. The source was practically a tone generator whose frequency had to be adjustable. And the filters were electronic filters, which people had long since been able to calculate. The problem was something quite different. The problem arose because, when using the vocoder synthesizer as a standalone device, one no longer knew how to control it. The input channel was gone. There was no longer a transmission situation. That is, what input information must I give to the synthesizer so that it produces speech somehow? This question was really answered only with the arrival of computers, but at this stage we are still far away from that. For this reason, the 1950s and early 1960s were characterized by experiments with how synthesis could be controlled. There was one pioneer in this area, the Swede Gunnar Fant, who during this period, inspired by a stay in the United States, created very interesting solutions. These can be shown here in the form of later analog devices. There was OVE I, whose principle can be recognized in this device. The idea here is that vowels are characterized by certain maxima in the spectrum, which are traditionally called formants in phonetics. The first two formants, that is, the first two maxima in the whole spectrum, are especially important for understanding a vowel. In OVE I, and also in this reconstruction, a formant chart was simply used as the input option. This formant chart can then be used, with the help of a pointer, to set the two formant frequencies, and then one hears the corresponding vowel. This old tube device, dating from 1962, no longer functions entirely as it should, but one can still recognize the principle a little. One switches on the tone generator and can then combine the two formants up here with the pointer. From today's point of view, of course, that is not exactly sensational, but at the time it was. In the end, it was proof that with these means, one could produce vowel structures that could genuinely be distinguished perceptually. We have just seen the synthesizer for vowels that goes back to Gunnar Fant's OVE I. Gunnar Fant developed this idea further and created the possibility of specifying different parameter trajectories on a film by means of a reading device. If one looks at it here, and if one knows what the specifications were, one can see that 4 formant frequency trajectories are given, along with the corresponding intensities, and so on. Naturally, this can be used very nicely for experimentation and for perception experiments with the speech synthesized in this way. This device here is again a commercial reconstruction of OVE I by an American company, and this commercial device was acquired at the time for the Phonetic Institute in Hamburg for the preparation of a dissertation on vowel perception. These different possibilities for controlling a synthesizer naturally also played a role here in Dresden. Walter Tscheschner made his own contribution with the so-called potential field control. With it, one could generate contours of vowel spectra, and these contours then serve to control a vocoder synthesizer. The corresponding setup, which by then had also been realized with transistors, was simply called Sen-I. Sen-I existed in two stages of development, essentially using germanium transistors. In a further expansion stage, it could also be controlled by punch tape. That was already a great step forward. These punch tapes were then still produced offline in a computing center. But with that, we were already just before the threshold of including computer technology. When the time came and process computers became available, which could be placed directly in the laboratories, a combination arose from the technology of Sen-I, and such a process computer, at that time from the Robotron R4000 family, in the form of a synthesis terminal for this process computer. A small series was built, and 3 of these are preserved down here. RO-SY, the Robotron synthesizer. RO-SY was used in various places to try out what could actually be achieved with this new technology. That was at the time a central question worldwide. One could produce a little speech in various places. Not very intelligible, but still. And people were looking for possible applications because these devices, as one can already see, were simply still very expensive and complex. The solution that suggested itself was the announcement system, which would stand somewhere in a central office, for example, the time announcement at the postal service or something similar. For that reason, the demonstration of these devices in announcement systems played a major role. ROSY was presented at the Leipzig Spring Fair in 1978 in a timetable information system that could say when the next train to Berlin would leave, for example, if one entered the postal code of the destination by telephone, practically via a tone dialing procedure. Similar intentions were obviously pursued in the Federal Republic of Germany at that time, to draw the parallel. There too, the aim was to produce such synthesizers as terminals for a host computer. We are fortunate to be able to show the corresponding device as well. This was a development of the Research Institute of the Federal Post Office at the Telecommunications Engineering Central Office in Darmstadt. It was called SAMT, and this synthesizer here, SAMT-32, was used in Karlchen. Karlchen was likewise a timetable information system, which 1 year later, in 1979, was publicly accessible in the Federal Republic of Germany and attracted a great deal of attention. It differed, as indicated by the number 32, in that in contrast to RO-SY, this device could serve 32 subscriber channels in parallel. That means that there were very high requirements for real-time behavior here, which was not the case with ROSY. In this respect, more digital technology was already used here than was the case 1 year earlier at Robotron. At that time, comparable stages of development still existed. In the GDR, as is well known, the available computing capacity could no longer keep pace. That means that in the 1980s, the performance of the available computer technology was no longer such that one could speak of competitiveness. In synthesis, we therefore limited ourselves to what was feasible, and that was still a great deal, because microprocessors had meanwhile become available. With microprocessors, one could make wonderful, embedded applications of speech synthesis. For that reason, the further development can also be seen in this cabinet, because the devices were simply much smaller. In the end, what RO-SY could do could be housed on such a circuit board for a microprocessor system. The whole thing then became smaller and smaller. There were interesting applications, especially in technology for the blind. Here you can see such a device. It is a pocket calculator for schools for the blind. Electronic pocket calculators were being introduced at that time, and people wanted to use pocket calculators at schools, for the blind as well. For that, however, they needed speech output. That was a very interesting development project at the time. Around 1990, semiconductor technology had progressed far enough that what had previously been on such a circuit board could be placed on a chip. This was still done in cooperation with the Dresden Fraunhofer Institute IMS2. By then, however, personal computers were becoming more and more powerful. Computing power improved, and above all, the available storage capacity increased enormously, so that in the end, no additional hardware was required anymore in order to perform speech synthesis. That means that synthesis disappeared into the PC, and as a result, speech synthesis has by now become a completed collecting area. The exhibition room we are now entering is devoted to speech analysis and speech recognition. Anyone who knows a little about this will say, well, this is all algorithmic, and in the end, computer programs, so there is not much one can show. That is correct. For this reason, this part of the exhibition is also somewhat more modest. On the topic of hearing, we naturally have various models of how it works in humans. As far as analysis technology is otherwise concerned, classical acoustic measurement technology is mainly used here, so there is not much special to show that would have been intended specifically for speech. What we nevertheless like to show here, in view of the tradition of this house, is a loudness meter according to Barkhausen. Heinrich Barkhausen plays a major role in Dresden as the founder of weak current engineering. He was appointed to Dresden in 1911. For him, acoustics always belonged to weak current engineering. He dealt a great deal with acoustic questions, among other things with the phenomenon that, at that time, there was no unit of measurement for the perception of loudness. He then took action and invented the first loudness meter in 1927, and we are very proud that we also possess an example of it here. Apart from that, as I said, not very much happened before the computer age, with the exception of one device, which today really has to be called spectacular. Like the vocoder, it goes back to activities at Bell Laboratories during the Second World War and stood under the broad theme of visible speech. That is, making speech visible in the form of spectrograms. At that time, an analog measurement technique was developed which produced astonishing results. In the end, speech could be represented in a form which, one really has to say, can today of course be implemented somehow on every smartphone, but which at the time was an enormous computational and technical effort. Namely, the production of such diagrams. In these diagrams, time runs horizontally along the bottom, frequency is plotted vertically, and the intensity of the speech signal at each point in the time-frequency plane is represented by a gray value, or later today more often by color coding. But even these grayscale images are very impressive. They were produced on a so-called Sona-Graph. The Sona-Graph was, after the war, the commercial version of this experimental setup for visible speech at Bell Laboratories. It was made by the K Electric Company. The K Sona-Graph was the device that one had to have at that time in phonetics and in speech technology. We have several examples standing here. This one here is shown with the cover removed, so one can roughly see what happens. The basic technique used here is, in itself, the tuning tone method. It was invented in Germany in this form in 1927 by Martin Grützmacher, and it is based in the end on analyzing a signal by obtaining spectral sections of it through the use of a relatively narrow band filter. In order to be able to do this over the whole frequency range, this filter must be tunable. One therefore needs a tunable, relatively narrow band filter. This principle was applied here in this Sona-Graph by using a drum on which this special paper was stretched, on which the spectrogram was to be drawn. In addition, there is a writing stylus that can move up and down. In the initial position, it is at the bottom. What is so ingenious and at the same time simple about this invention is that on the same axle as this drum, there is a magnetic disc under the cover. On this magnetic disc, a speech utterance of about 2 seconds can be stored, so a word fits on it quite well. And now the following happens, basically quite simply. I set my tunable filter to the lowest frequency, let us say 100 Hertz, so that the calculation is easy here. Then I run through this recording once. That means that at the output of my filter, I see the energy course in the frequency range around 100 Hertz. The output of this filter is connected through an amplifier with this writing stylus. That means that during one revolution, the device writes the lowest line of this image. Now it is already quite simple. For the next revolution, I set the filter up to 200 Hertz and lift the writing stylus by one line. That means next rotation, second line written, 200 Hertz. Then it becomes boring, because the next round is, so to speak, 300 Hertz, third step for the writing stylus, and so on. What does one learn from this? It is very simple to produce this image, but it does not happen in real time. That means that the device has to rotate as many times as there are lines here. It takes minutes to produce such an image. But in the end, one has a perfect reproduction of the content of the speech signal. One can see here at low frequencies how the formants develop during vowel articulation. One can see where plosive sounds are, because there one sees such sudden energy onsets. One can see where fricatives are, because relatively high frequency components must be present there, for example here, and so on. This was a great breakthrough and a great help for all of speech research. Soon after the invention of this device, the question arose whether one could not also recover the speech signal from this coding. That was the idea behind the so-called playback device. It has a high didactic value. If someone looks at this gray value pattern and asks, "Is that supposed to be speech?" one can really say, "Yes, I can play it to you." For that reason, shortly after the war, so-called playback devices were already developed in the United States as demonstrators. A reconstruction of one of them also exists here, and we will now look at it. So, we are now back once more in the area of speech synthesis, because here I can show that spectrograms can be resynthesized successfully. As I said, that was an idea that had already arisen shortly after the war among the inventors of visible speech. The device I am showing here was intended to make this effect usable for Walter Tscheschner's lecture. Tscheschner was appointed in 1969, which means that this reconstruction dates from the early 1970s. One can see here a drum, and this drum can rotate, and a spectrogram is attached to the drum. It looks relatively coarse, and that is all right. Here, the grayscale coating of the spectrogram has been coarsened into a black and white pattern. That is sufficient for the intended purpose. And it shows once again how redundant our speech actually is. This black and white pattern is then scanned by photodiodes located up here, where one can see it glowing. This information is then supplied to the synthesis channels of a vocoder synthesizer. That is essentially the whole explanation. Now one only has to switch on the synthesizer. So that is already the whole thing, but at the time, it had at least an extremely high didactic value and was used very successfully by Walter Tscheschner in lectures and in various general educational talks. And we are pleased that this device still functions today and that I can demonstrate it to you here. With that, I have reached the end of the short tour through the Historical Acoustic-Phonetic Collection. Thank you for your attention.